Welcome to The Explainer. Today, we're going to do something that honestly feels a little bit like magic. We're taking a seemingly complex block of MATLAB code and we're going to completely demystify it. But we're not just going to read it like a dry, boring manual. Actually, scratch that. Let's treat this code as an act of digital world building. We are essentially constructing a miniature universe inside a computer, step by step, all just to simulate an electromagnetic field.
Okay, let's dive into this. How exactly do we write code to see the invisible? Because in the physical world, electromagnetic fields are constantly surrounding us, right? They're bending, shifting, and reacting to objects, but we literally cannot see them with the naked eye. So engineers and physicists face this major physical problem. How do we map and visualize these invisible forces so we can build better electronics or antennas or power grids? Well, the answer is simulation. And achieving that requires this absolutely beautiful intersection of geometry, physics, and computer programming.
So here's our game plan for the explainer today. We're doing this in 4 phases. Phase 1, setting up the grid. Phase 2, coding the physics. Phase 3, the zero field zone. And phase 4, rendering the final visual.
All right, phase 1, setting up the grid, building the universe. Before we can do any physics, we've got to build a blank canvas. And we do that by clearing out the computer's old memory with the quick CLC, clear, close all. Now, with a clean slate, we immediately set the ground rules and the size of our universe. We do this by declaring 4 simple variables. We've got r set to 1.0, that dictates the radius of the conducting sphere we're dropping into our world. Then there's e0 set to 1.0, representing the baseline strength of the uniform electric field pushing through the space. Next, n is 30, which acts as the resolution, or kind of like the fidelity of our simulation. And finally, lim set to 2.0 creates our spatial boundaries, basically the physical limits of our digital box along the x and z axes. So, these 4 parameters, they're basically the DNA of the simulation we're about to build. Knowing our boundaries is great, but the computer needs physical coordinates to actually calculate the math, So by passing our boundary limits into the linspace function and then feeding that right into the meshgrid command, we're essentially rolling out this massive sheet of digital graph paper across the x and z axes. That meshgrid command takes those 1D lines and weaves them together into a 2D grid. So now we have an arena, a specific set of coordinates where our physics simulation can actually take place. Now, what's really interesting about this slide is why we immediately convert that beautiful X and Z graph paper into something totally different. The code uses the math commands sqrt and atan2 to translate our Cartesian grid into radial polar coordinates, specifically r for radius and theta for angle. Why do we do this? Well, because physics equations involving spheres absolutely hate squares. A sphere is fundamentally round, meaning the electric field behaves based on how far away you are from the center and at what angle. So by shifting into polar coordinates early on, we make the upcoming physics math vastly simpler to compute.
Moving right along to phase 2, coding the physics. This is where we inject the laws of nature right into our grid. Okay, this is the heavy lifting of the entire script. These 2 equations dictate exactly how the uniform electric field bends and mathematically reacts to the presence of our sphere. ER handles the radial component, how the field pushes outward, while E theta handles the angular component, describing how the field flows around the sphere. And notice that term in the middle, r cubed divided by r cubed. That right there represents the physical interference of the sphere. As your distance, r, gets closer to the sphere's radius, r, that interference term gets larger and larger, causing the uniform field to dramatically warp and bend around the physical object. It's super cool to see the math do that. Now, we've got our physics calculated perfectly in polar angles and radii. But remember that digital graph paper we laid out earlier? Our computer screens and the plotting tools we're going to use, they operate in Cartesian x and z grids. And since we can't easily plot polar math directly onto our square pixel displays, we've got to map those ER and E theta values back into Cartesian EX and EZ vector components using some basic trigonometry. We did the complex physics in the math-friendly polar space, and now we just translate it back into computer-friendly display space.
Up next, phase 3, the zero field zone. Time to code a physics reality.
So our mathematical formulas from that last step, they're technically perfect, but pure math doesn't automatically know about real-world material properties. So we forgot one crucial real-world rule. We have to manually code in a specific physics reality about perfect conductors. Now, if you spent any time programming, you know seeing a nan pop up on your screen usually means a massive error, not a number, right? It usually means your code just crashed or divided by 0. But here, no way. It's about to be used for a brilliantly clever physics trick. So, the crucial point is how this code enforces a fundamental law of electromagnetism. Electric fields literally cannot exist inside a perfect conductor. The charges inside instantly rearrange to cancel out external fields. To simulate this, the script finds every single point on our grid where the radius r is less than the sphere's radius r. For those internal points, it sets the electric field vectors Ex and Ez to NaN. By declaring these values not a number, we're forcing the program to literally draw nothing inside the sphere. It's kind of lazy, honestly, but it's a perfectly accurate way to represent real-world physics constraints.
And for our grand finale, Phase 4, rendering the final visual. Let's turn on the lights. Let's move to and see how this builds our final plot. Step 1 is normalization. Think about it. If we plotted the raw field vectors, the arrows near the sphere would be absolutely huge, and the ones far away would be tiny little dots. By dividing the vectors by their magnitude, we force every single arrow to be the exact same length, making the direction of the field beautifully clear. Then, step 2 uses MATLAB's quiver function to actually draw all those tiny normalized directional arrows onto our grid. Finally, step 3 uses a circle made of 400 points to fill a solid visual gray circle right in the center, representing our physical metallic conductor.
Of course, a simulation isn't truly complete until it's formatted to communicate clearly. These finishing touches are all about aesthetics. We added text label directly onto the gray sphere so anyone looking knows for sure it's a conductor. We set clear X and Z axis labels and drop it a nice overarching title. But honestly, the most vital formatting command here is axis equal. Without that tiny command, MATLAB might stretch our plot to fit a rectangular window, making our perfectly calculated sphere look like a squished oval. Axis equal locks the aspect ratio, keeping our mass geometrically true to life.
And this brilliantly illustrates the final payoff of all our hard work. The script wraps up with the print command, taking our completely rendered universe out of the software and saving it into a high-resolution 300 dot per inch PNG image file. It perfectly bridges the gap between complex theoretical physics running in computer memory and a tangible, shareable image you can drop straight into a scientific report or a deck.
So, we just stepped through a total masterclass in digital modeling. From setting a grid to applying polar physics, accounting for constraints, and rendering the output, we literally mapped the invisible. But I want to leave you with this provocative thought. If this entire universe we just built fits into about 40 lines of code just to simulate a perfect, uniform sphere, what would it take to simulate the real world? Because engineers use this exact foundational logic to design complex technologies, from aerospace radomes to electric vehicle battery systems. If 40 lines does this, imagine the sheer scale of the code required to simulate the chaotic, asymmetrical, incredibly complex reality we live in every single day. It is truly mind-boggling to think about. Thanks for exploring this with me today.